In this video, we'll look at things that are related to trigonometric inequalities. Let's use the first example to demonstrate how to solve a simple trigonometric inequality. This is a simplified version of a past AMC12 problem. The question says, we randomly choose a point within the rectangle where x is from 0 to 1/2 and y is from 0 to 1. Then what is the probability that sine pi y is bigger than cosine pi x? In order to find the probability, what we need to do is to identify the region where this trigonometric inequality holds, and then the probability is just equivalent to the ratio between that region, between the area of that region and the whole area, which is 1 times 1/2, which is 1/2. Okay, all right. There are different ways to solve this trigonometric inequality. What I like to do is to first of all transfer them into the same trigonometric function. Since here we have two trigonometric functions, one sine and cosine, so we can first transfer them into either both sine or cosine. So I will go with sine. Alright, now first of all I get, because this one, cosine, we use the relation how you go from cosine to sine. This one is just equals sine pi over 2 minus pi x. Okay, and then all we need is we want to find this sine pi y is bigger than sine pi over 2 and minus pi x. Now, if we recall the sine function, we know the sine is strictly increasing within the range negative pi over 2 to pi over 2. Remember, that is the domain, the range where the inverse sine function, arcsine, is defined. Alright, then what I want to do is, I want to put the inputs pi y and 2 pi minus pi x, somehow I want to put these two into this region. And then we have sine, say, one is bigger than the other, it's just equivalent to the input is greater than the other, right? Okay, now let's check the range of these two inputs. Because x is between 0 and pi 1/2, then pi over 2 minus pi x, this one is already belongs to the desired range domain, which is from 0 to pi over 2. If we look at pi y, but however, y is from 0 to 1, so pi y belongs to 0 to pi, which is not exactly within the range, right? Part of it is out of it. Therefore, what I want to do is I will look at two cases. Let's look at two cases. So case 1. If y is between 0 and 1/2, then we'll have pi y belongs to the desired domain. So that's 0 to pi over 2. And therefore, for this case, then we just use the function strictly increasing between negative pi over 2 to pi over 2. We'll just get pi y is greater than pi over 2 minus pi x, which implies the xy is bigger than 1/2. Okay, let's see. Let's draw this region within the rectangle. Now y is between 0 to 1/2 is here, and x plus y is bigger than 1/2. Okay, this is the line that is x plus y is equals to 1/2. Okay, so bigger than 1/2 is right here. So this is the region within this triangular domain. So that is from the case 1. Now let's put this is just case 1. Okay, so we got this part is from case 1. Now let's look at case 2. That's when y is between 1/2 and 1. Let's look at case 2. Case 2. If y is between 1/2 and 1. Now for this case, then the pi y belongs to pi over 2 pi. that is outside of desired region, what I'm going to do is I'm going to use the trigonometric identity to transfer this back to the desired region. Okay. So I'll use the sine pi y equals sine pi minus pi y. Alright, then sine pi minus pi y, this one will belong to this from 0 to pi over 2, that is within this nice region. Okay. Alright, so from here I just get sine pi minus pi y is greater than sine pi over 2 minus pi x. Okay, now both of them are within this range from 0 to pi over 2, and then we have to have pi minus pi y is greater than pi over 2 minus pi x, which is equivalent to saying the y is less than 1/2 and plus x. Okay, now let's look at what we have here. Y, first of all, y is between 1 and 1/2 to 1. Now, if y equal to 1/2 plus x is right here, so this is the line. Right, so this is the line that is y equals 1/2 plus x. Now y is less than that, so it's below it, so it's right here. Okay, so that's the one which is from case 2. Now if we combine, okay, so that's the case 1 and the case 2. Now if we combine case 1 and the case 2 together, we combine them together, and the area, you see, the area of this one equals this is just 1 over 4. Alright, so that's the design region is 1 over 4, and we get the probability is 1 over 4 over 1/2. This obviously is 1/2. So we get the probability is 1/2. That is just the ratio of just the fraction of the whole thing that is within this triangle. That's 1/2. Next, let's prove an important trigonometric inequality. This inequality says, for theta between 0 and pi over 2, we always have sine theta is strictly less than theta and strictly less than tangent theta. Okay, let's prove this by a simple geometric approach. Okay, so here we have a unit circle on a coordinate plane. This is the angle theta. And then, if we recall the definition of radian, so here we use the unit of radian. So if we recall the definition of radian, because the unit circle, then theta just means the side length, the length of the arc. So this is theta, which equals this arc length. Alright, and then what is sine theta? For sine theta, if I draw, let me mark this point as A. So if I draw a height from A to this radius, let's say this point I put as B to OB. Alright, and then this one equals sine theta, just by definition sine theta. Now, this is the height perpendicular, and obviously it is less than this AB, which I put is L, right? Okay, so sine theta is less than, which is the leg of this right triangle, the leg less than hypotenuse, and meanwhile L is a straight line connecting AB, which is, of course is less than this arc length, because the line segment is the shortest path connecting 2 points, right? Okay, so proof. So here we get the sine theta, which equals this height, which is less than the AB. Okay, less than AB, and AB is less than this theta, which is arc length. Alright, so we have proved this half, sine theta is less than theta. Now let's look at the other one. Okay, so this part is done. So we have established this one. Now let's look at the other half. How we prove that theta is less than tangent theta. For that one, we are going to use areas instead of arc length. Now let's prove the second half, theta is less than tangent theta. For this one, we are going to use areas instead of arc length. Now let's go back to this unit circle. This time, let me draw a height from B, it's perpendicular to here, and extend OA and intersect to this. Let's denote this by C. Okay, all right. And then, by definition of tangent theta, well, tangent theta equals basically the ratio between the opposite leg and the adjacent leg. So if this is 1, we'll get this one equals tangent theta. Okay, now if I look at triangle COB, this is 1 and it's right triangle, this is 1 the tangent theta. So from here I get the area of triangle CBO equals 1/2 times tangent theta. Okay. This one represents the area of the triangle OCB. Now let's see, how can we express theta? Well, let's look at the sector. Let's look at the sector. What is the area of the sector? Okay. So we have here, we get the area of the sector, that's OAB, OAB equals, which is theta over 2 pi times the total area, which is pi, so that's theta over 2. Alright, theta over 2 represents, we know theta itself represents this arc length, and theta over 2 equals the area of the sector OAB. Now, if you compare the area of OBC and the area of OAB, obviously this one is greater because the sector is just part of it. So I have this one is greater than that, and this is greater than that. Now I cancel 1/2 on both sides, and this leads to what we want. So tangent theta is greater than theta, right? Based on comparison of areas. All right, so we derive this. The first half is related to our derivation of the first half, rely on comparison of line segments and arc length, and the derivation of this one is using the comparison of 2 areas. Now, let's see an important application of this inequality in calculus. Okay, so from this inequality, I can derive sine theta over theta is obviously less than 1 when theta is between 0 and pi 2, and is bigger than sine theta over tangent theta. Now, if you recall, the tangent theta is sine theta over cosine theta, and this ratio equals cosine theta, right? Okay, now, if I let theta, so cosine theta, so this is the graph of cosine theta. If you recall the graph cosine theta, this is theta, and here is cosine theta. This is 0. Now, if I let theta become more and more like 0, so we have to let theta getting closer to 0. And then what I have is, what is where does cosine theta approach to? When theta, so theta approach 0, so cosine theta will just approach, if you approach theta approach to 0, and cosine theta, the graph is continuous, cosine theta just approach to cosine 0, right? But cosine 0 we know equals 1. Okay, so then you see, this is like a sandwich. I have sine theta over theta is always less than 1, but meanwhile, if theta goes down to 0, we know cosine theta, this is bigger than cosine theta. Cosine theta goes down to goes to 1, right? If I rewrite this, we have the sine theta over theta is less than 1, but it's greater than cosine theta. But if I let theta goes down to 0, this one goes down to cosine 0, which is 1. And this tells us the limit. Okay, so this is notation of limit. This means when theta approach 0, how does sine theta over theta change? It tells us it just go to 1. Okay, the right hand side is 1 and left hand side go to 1, so we get this 1. Okay, so this limit is important because from here people can derive. If you look at the derivative of sine theta, this equals cosine theta. This one means derivative in calculus. The derivative of sine theta equals cosine theta, which is derived from this limit. And this limit itself is derived from this inequality.